Okay, so today we will start the non-Newtonian fluids. Okay, so before starting the non-Newtonian fluids, I just recall the about the Newtonian fluids. So what is the Newtonian fluids? Newtonian fluids are the fluids which follows the Newton's law of viscosity. Okay, so Newtonian fluids are the, and what is the Newton's law of viscosity? Basically, I have explained you a hypothetical experiment where there are two parallel plates situated to h distance to each other, and a fluid is present in between the plates. This is the y-axis, this is the x-axis. Fluid is present between the plate. The distance in the between the plate is h. So you start to move the bottom plate and keep the upper plate at the stationary condition. Okay. So the force required to move the bottom plate, you plot the force required to move the bottom plate and the divide by the area to the velocity divide by to the velocity divide by the higher distance between the two plates. Basically, you have done the experiments with different velocities v1, v2, v3, v4, and for different velocities you require the different forces f1, f2, f3, f4. So now calculate F by A. A is the area of the plate. And divide the velocity with the height h. Okay, v1. So this is a hypothetical experiment. So once you get these values, just plot F by A versus V by H. You will get, for most of the fluid, you will get the straight line. So if you get the straight line, that means F by A is proportional to V by H. And so F by A is the shear stress that can be represented by tau xy. That should be equal to minus mu dV dvx by dy. Okay, so this is the Newton's law of viscosity. Okay, so most of the fluid follow this rule, and you will find the graph passing through the origin, and this is a linear line. So this is the Newton's law of viscosity. But there are several fluids which will not obey this rule. So these type of fluids called the non-Newtonian fluids. Okay, so non-Newtonian fluids are the fluids which do not obey the Newton's law of viscosity. Okay, so if you again plot the shear stress versus shear strain graph, so this is the shear stress tau xy versus dvx by dy. So for Newtonian fluid, you will get a straight line passing through the origin, but sometime you will find the graph which will not a linear, but passing through the origin like this. Sometime you will find this type of graphs, and sometime you will find the linear graphs which will not passes through the origin. Okay, so this is the first curve, this is the second curve, this is the third curve, and this is the fourth curve. Okay, so there are different type of curves. These are the second, third, and fourth. These are the most common non-Newtonian fluids behavior. Okay, and there are more complex fluid behavior also, which we will discuss later in this subject course. Okay, so first we will discuss the these type of fluid behavior. Okay, so first curve represent the Newtonian flow. That means what is the Newtonian flow? When shear rate, that is dvx by dy, will where the shear rate will not depend upon the viscosity, or viscosity will not, it is written in the opposite way, the viscosity will not depend upon the shear rate. Here viscosity is the slope of this curve. Okay, that is a constant value, so viscosity will not depend upon the value of shear rate. When viscosity is not depend on the shear rate. Okay, so this is the first type of curve, most common fluids, Newtonian fluids. Now second are the non-Newtonian fluids. So non-Newtonian fluids. In non-Newtonian fluids, you have the different types of fluids. So the second curve, curve second, that represent the pseudoplastic fluid. Okay. Okay. So what is the pseudoplastic fluid? Here, if you check this graph, okay, so the viscosity is the slope of the curve, so you will find the slope of the curve is changing with x-axis. Okay, so the here the slope of the curve, the viscosity is dependent upon the shear rate, and second point is the value of the viscosity will reduce with the increasing of shear rate, means fluid will become the thinner, है ना? So viscosity will reduce with increasing the shear rate. So this type of behavior is generally represented by the different type of polymeric melts and the polymeric solution. Even sometimes paints, fluid like paints also represent the pseudoplastic behavior. So when you increase the velocity of the fluid, the viscosity will reduce. Okay, so fluid become the more thinner. So in most of the plastic material, you will find the pseudoplastic fluid behavior. So first point, viscosity depends upon depends upon the shear rate. Shear rate means dvx by dy, and second point, viscosity reduces with increasing shear rate. Okay, so as you increase the shear rate, the viscosity will reduce. Okay, so this is the main point of the pseudoplastic fluid. Now, after pseudoplastic fluid, you have the third curve, which represent the dilatant fluids. So the third curve represent the dilatant fluids. Okay, so what is the dilatant fluid? Here again, if you check the third curve, you will find that the viscosity is changing with changing the value of dvx by dy. Viscosity is the slope of the curve. So that is continuously changing with changing the value of dvx by dy. So viscosity will depend upon the shear rate. And the second point is, as you increase the shear rate, the viscosity will increase. That means when you increase the velocity of the fluid, the fluid become the more thicker, and that will become more viscous. Okay, so there are several type of semi solid material which will follow this rule. Okay, so like the charcoal, okay, or any semi solid material, you will find semi solid materials follows generally this rule. Okay, when you have the very less shear rate, very less velocity, they will flow very easily. But when you increase the velocity, then you will find the you will face the more resistance. Okay, so the material become more viscous. Okay, so viscosity depends upon the shear rate. Means dvx by dy. Second point, viscosity increases with increasing shear rate. Okay, so these are the two main points. Now you have the fourth curve, that that is the this curve. So in the fourth curve, it is similar, it is also a linear curve. Okay, basically the fourth curve is a linear curve, but it does not passes through the origin. Okay, that means it requires some initial force to flow. Okay, so this is called the Bingham plastics. This type of fluid is called the Bingham plastics. So Bingham plastics are the material which requires some initial force to flow. Okay, so the it will like the gel. Okay, gel type like toothpaste. Okay, so these are the example of the Bingham plastics. So these required initially it will remain without any shear rate. It will remain as a solid material. When you push the material, when you forces the material up to a certain amount of force, more than a certain amount of force, then it will start to show the fluid like behavior. Otherwise it will be remain as a solid material. Okay, so this is the Bingham plastic. These are the example of Bingham plastics. So curve 4 represent the Bingham plastic. Okay, so These required some initial force or shear stress is required for flow. Otherwise it will move like a solid block. Okay, so in toothpaste you can see that you will require initial force, then only it will flow, otherwise it will remain in solid. And the where the shear stress value is less, they will come as a solid block. Okay, so if you see the toothpaste, so it will come as a tube like structure. Why? Because shear stress values are higher at the boundaries and lower at the middle point. So at middle point it will remain as a solid block. Only at the boundaries it will move as a fluid. Okay, so only the boundary of the paste will act as a fluid. The middle part will act as a solid material. Why? Because at the middle part you have the lesser shear stress, so it will remain as a solid material. Only the at the boundaries where the stress values are very high, shear stress values are very high, that will work as a moves as a fluid. Okay, so these are the four different type of non-Newtonian fluids. There are other types of non-Newtonian fluids also, but these are the main types. And most of the fluid behaves in the different behaves more than one type of, most of the non-Newtonian fluids behaves more than one type of non-Newtonian, show the more than one type of non-Newtonian behavior based on the range of shear rate. Okay, so there are some fluids like polymeric melts. So if you plot the shear stress versus shear viscosity versus shear rate, this is the viscosity. So viscosity mu versus shear rate d Vx by dy curve. So at very low shear rate, it will remain constant. Then it will slightly increase. Then again decrease for a very long shear rate range. Then at very high shear rate range, it will again become constant. Okay. Now if you compare this graph, so here the viscosity is constant. From this region, viscosity is constant with the shear rate. So it is a Newtonian region. So at this region, fluid behaves as a Newtonian fluid. At this region, where viscosity slightly increases with the shear rate, that is the dilettante region. Okay, so this is the dilettante region. From here to here, viscosity reduces. In this region, viscosity reduces with the shear rate. So this is the pseudoplastic region. And again, at very high shear rate, you have the constant viscosity. So this is again the Newtonian region. Okay, so you have the different types of flow region and the different types, different shear rate ranges. Okay, so similarly, most of the several non-Newtonian fluids shows the very complex behavior, and they show generally shows the different type of non-Newtonian behavior at the different ranges of the shear rate. Okay. Now, one question arises that why the fluid shows the non-Newtonian behavior. Okay, so simple fluids like water, oil, they will always show the Newtonian behavior. So why does fluid shows the Newtonian? Why the what is the basic definition of fluid? When the molecules start to move. Okay, from the physical forces, the intermolecular forces between the molecules are significantly lower, then they will start to move from the influence to each other. Okay, when the molecules, the distance between the molecules increases and they will start to move then it will call the fluids. Okay, or generally most of the fluids, even the gaseous fluid like air, nitrogen, oxygen, helium, hydrogen, or different type of normal fluids like water, oil, different type of solvents, they all shows the Newtonian behavior. So most of the fluid shows the Newtonian behavior. But why some fluids shows the non-Newtonian behavior? Based on their complex intermolecular interactions. Okay, so I'm giving you the example why some fluids shows the non-Newtonian behavior. Okay, so basically non-Newtonian behavior is always due to the sum of the complex interaction between the intermolecular interactions. Okay, so most of the non-Newtonian fluids are the very complex fluids like polymeric melts. So first we will take the example of polymeric melts. So polymers are the macromolecules. They are the long chain hydrocarbons. See, so generally most of the suppose most simple polymer is the polyethylene. So it contains the single carbon chain like this. This is the polyethylene structure of the polyethylene. So and the number of molecules in this structure, number of carbon atom in this chain is nearly more than 10,000. Enough. If you check the polyethylene, commercial polyethylene, so they started the range of number molecular average weight should be more than 10,000, and for the normal injection mold polyethylene, they will around 2 lakhs to 5 lakhs. So this number of the 2 lakhs to 5 lakhs carbon atoms will attach to each other to make a single molecule of the polyethylene. Okay, so these are basically the single structure polymer. So generally polymers are macromolecules and the geometry of polymers are the ribbon type molecules. Okay, so basically if you check the polymers, you will see the polymers are the ribbon type molecules. Okay, so this is the basic structure of polymers. So they are not the simple molecules, they are the macromolecules, very big molecules. And generally the polymer in the carbons atom and the other atoms will arrange in a linear structure in a series, and it will make a ribbon type of structure. Okay, now suppose you are putting a shear force on the this ribbon type structure. Suppose you are putting the F force on the ribbon type structure in this direction. This is the X direction. Okay, in the X direction. Okay, so here you have a plate which is in the stationary condition. From the top of the plate, like the Newtonian behavior, Newtonian experiment, you are giving a shear force of the magnitude F in the X direction. Okay, so what will happen? The molecule starts to move in the X direction due to the force. Now you can see that due to the ribbon type of structure, these molecules are entangled to each other. Okay, so they have the entanglement to each other, and most of the polymers are, even the generally all polymers are non-crystalline materials. Okay, or the semi-crystalline materials. So what is the semi-crystalline material? Semi-crystalline means only some of the part of the molecule is arranged in the crystal structure. Most of the part of the molecule is not arranged in the crystal structure. So if you see the polyethylene molecule, you will find that they have this type of crystal structure. So this is the crystalline part of the molecule, and rest of the amorphous part. Amorphous means where the molecules are not arranged in a systematic way. That is the amorphous part. And crystalline part means where the molecules are arranged in the systematic manner. That is the crystalline part. Okay. So if you say the real solids, so real solids are always a crystalline material. Okay. So crystalline means they are the molecules are arranged in a systematic manner. So most of the polymers are semi-crystalline material or amorphous material. Means the molecules are has the so much large size that they cannot arrange in a systematic manner. Only partial part of the molecule will arrange in a systematic manner. Okay. So due to the amorphous characteristic of polymer, the molecules tends to entangle to each other. So they will entangle to each other basically. You know, here you will find that this chain will entangle with the other chain, then it will entangle with the other chain. So they are entangled to each other. Now, when you start to apply the force on the system, suppose you are starting to apply the force on the system. So what will happen? Initially, the your force is, suppose you are progressively increasing the force, and initially you start to give a very less force, then you are increasing the force. So what will happen? At the very low force, this whole bulk will act as a solid material. They start to slightly move as a material. Okay. So entanglement will be remain as the same. The crystalline part will remain as the same. Only they will start to slightly move. Okay. As a bulk, bunch of material, bunch of molecules. Okay. So you will find at very low shear rate, it will show the viscosity will remain constant for a very low range. Okay, very low range when the force is very less. So it will not affect the structure of the material, structure of the molecules, and it will just show the slight deformation. Okay, entanglement will remain same. Now after that, when you increase the force, you will find the molecules starts to stretch to each other. Due to this entanglements, they will start to stretch. Okay, when they will start to stretch, the viscosity will increase. Okay, you will find the less resistance to flow because the molecules are start to stretch each other. You know, this due to this entanglement, because they are coupled with each other due to the entanglement. This is like the ribbons. Okay, now after that, when you again increase the force, then due to the differential force of each layer, the molecules, the entanglement start to open. है ना? Due to the because these are the bunch of the ribbons of the molecular ribbons. So when you start like noodles, okay, bunch of the noodles. When you force the noodles with very high shear rate, then the noodles start to the entanglement between the noodles start to remove. So once the entanglement start to remove, the viscosity will reduce because the resistance will reduce. Then the viscosity will reduce. Okay, because now the molecules are unentangled. Okay, so they will start to arrange in a parallel manner. Okay, and at very high shear rate, due to you have removed all the entanglement, then again it will become the viscosity will become the resistance will become constant and viscosity will become constant. Okay, so you will see that how the complex structure of the you have seen that how the complex structure of the polymer will affect the its its rheological or its flow behavior. Okay, so in the similar, this is the example of the polymeric melts. Similarly, if you see the colloidal solutions, okay, suppose you have the very dense colloidal solution like jam. Okay, so in that solutions you have the very big particles of the solid material, and in between you have the liquid. Okay, so what will happen At very low shear rate, the material will again behave as a bulk. Okay, but when you increase the shear rate, then the at very low shear, the material will remain as a bulk. It will flow as a Newtonian fluid. But when you increase the shear rate, the in between, the layers between the fluid layer between the solid particles, that will remove. Okay, so solid particles start to collide to each other, and the friction between the fluid and solid is lesser than the friction between the solid and solid bodies. Okay, once the surface of the solid and solid bodies start to rub each other, then the friction will increase very fast, and you will find that viscosity will increase with increasing the velocity. Okay, so this is the example of dilatant fluids. So similarly, you have the different type of complex fluid where the viscosity is not constant, and they will change, viscosity will change with increasing or decreasing the shear rate. For the normal fluid, viscosity is never the function of the shear rate. For normal Newtonian fluid, viscosity is the function of temperature only. At a given temperature, viscosity of water is constant. Okay. If you are saying that 25 degrees Celsius, you have the 1 centipoise viscosity of water. Okay. No matter how fast or how slow you are flowing, water is flowing. Viscosity of water is always constant. Similarly, for the air, the viscosity of air is 0.018 centipoise at 25 degrees Celsius and 1 atmosphere pressure. Okay, so it does not matter how fast or how slow air is flowing. The viscosity is of the friction force of air will remain always same. Okay, but for complex fluid, some type of complex fluid, due to the molecular structure of the material of the fluid or the intermolecular forces of the fluid, you will find that the fluid will behave strangely with the different shear rate. The viscosity of the friction forces will change with changing the shear rate values. Okay, even in the cycles, suppose this is the first cycle. Now you reduce the viscosity and again do the same experiment. You will find that it will not follow the same curve because now the values of entanglement is changed. Okay, so if you again do the same experiment with the same material, the viscosity will not remain the same as it was given in the first experiment. Okay, so you will get the different viscosities. So this is how the material will behave in very complex manner when you have the complex molecular structures. Okay, so now for designing the fluid flow equipment, you need the mathematical models. Okay, so for Newtonian fluid, it is represented by the Newton's law of viscosity. So rheological behavior or melt rheology of the or the flow behavior of the Newtonian fluids are represented by the Newton's law of viscosity. That is tau equal to minus mu, tau xy equal to minus mu dvx by dy. This is the most simple mathematical expression. Okay, in the fluid mechanics, this can be used to represent the Newtonian behavior of the fluid. Now, similar to this equation, you have to develop the we have to develop the mathematical models for the non-Newtonian fluids also, because the for non-Newtonian fluids also, when you design a equipment, when you design a pump or the when you design a pipeline, you need the some mathematical model which correlates the shear stress and shear rate. Then only you can calculate when you apply a force, what will be the velocities. Basically, this equation that is telling that when you apply a force, what will be the velocity. Okay, shear stress is related to the force and shear rate is related to the velocities. So similarly, in the and for non-Newtonian fluid also, you need some equations, some mathematical model which shows that what is the correlation between the shear rate and shear rate and the force applied or the shear stress. Okay, so there so the models will become more complex when you have this type of fluids. There are two more type of fluids which you should remember. One is the thixotropic fluid and one is the rheopactic fluid. Okay, so that you have also remember. I am writing here only. So four now. Fifth is the thixotropic fluid, and sixth is the rheopactic fluid. So these are the fluid where the viscosity is time dependent. So viscosity not only may depend upon the shear rate for non-Newtonian fluid, viscosity may also depend upon time. Okay. So in the thixotropic the viscosity increases with time. And in the rheopactic fluid, viscosity decreases with time. And why fluid behave in the thixotropic or rheopactic way? Why you have the some fluid which where the viscosity, even the you are not applying any shape force, the with time the viscosity will increase, and why the viscosity will reduce with the time? It happens when you have a reactive fluid. Okay, sometimes there is a fluid where the cross-linking occurs automatically due to the presence of the moisture in the atmosphere, like Femiquick type of fluid, where the material like gum. So if you left the gum at the atmosphere, the viscosity will slowly the molecules start to cross-link to each other, and then you have the viscosity will increase due to the partial cross-linking between the molecules. Okay, so with time, viscosity will increase. So that is the thixotropic fluid. Similarly, you have the other phenomena also when the molecular bond start to break down with time because the molecule is unstable. So there are fluids where the molecules are unstable and the molecules start to break down with time and make the smaller molecules, and then when it make a smaller molecule the viscosity is reduced. Okay, so this type of fluids is called the rheopactic fluids. Okay, so these are also two different type of fluids, thixotropic and rheopactic. Apart from this, you have the pseudoplastic fluid, dilatant fluids, and Bingham plastic fluids. And these are the most common type of non-Newtonian fluids. Now comes again in the model. So you have the Newton's law of viscosity for the Newtonian fluids. Similarly, you need the model for the non-Newtonian fluids. So to make a mathematical model of the non-Newtonian fluid, there are different approaches. Okay, most simple and most accepted approach is the generalized Newtonian models. Okay, so mathematical modeling of non-Newtonian fluids. So most simple model is the generalized Newtonian models. So basically, the generalized Newtonian models are the type of models which are similar to the Newton's law of viscosity, but the viscosity is not constant. Okay, the model is same, only we are saying that the viscosity is not constant. So it will become the generalized Newtonian behavior models. Okay, so in the generalized Newtonian model, we represent the tau xy equal to minus eta multiplied by dvx by dy. Okay, this is the generalized Newtonian behavior model. Okay, so this is similar to the Newton's law. Okay, only difference is instead of mu we are writing the eta. Okay, so eta is called the apparent viscosity. Okay, and this is the function of eta is the function of the shear rate. Okay, so the difference is in the Newton's law of viscosity, mu is a constant. Here, eta is not constant. It is the function of shear rate. And now you have the different types of mathematical model inside the group of generalized Newtonian models. So based on how the eta will depend upon the shear rate, you have the different types of mathematical models. Okay. Okay, so first we will discuss the most simple model, that is the power law or the Ostwald-de Waal model. So the first model is okay. So in this model, we write the same equation known as generalized Newton's law, tau yx equal to minus eta dvx by dy, where eta equal to minus m, eta equal to m, not minus m, eta equal to m mod dvx by dy to the power n minus 1. Okay, or you can write this equation as a tau yx equal to minus m mod dvx by dy to the power n minus 1 dvx by dy. So this is the most simple model. This is also called the two parameter model. Why this is the two parameter model? Because here you have the two parameters m and n. So these are the constant. Okay, this is a two parameter model. Where m and n are the two parameters and these are the constant. Their values will be constant for a given fluid. Okay, so like Newton's law of viscosity is a one parameter model. In Newton's law of viscosity, you have mu as a constant. So it is a one parameter model. The power law is a two parameter model where m and n are the two parameters. Okay, n is also called the viscosity index. Okay, here n is also called the viscosity index. Now, how to remove this mod sign? Okay, so we will see first. We will see how to remove this modulus sign. So the rule is for removal of the modulus signs. The rule says if dvx by dy is positive, then the modulus sign, when you remove the modulus sign, the quantity will remain positive. If dvx by dy is negative, when you remove the modulus sign, the quantity will remain the negative. Okay. So first, if dvx by dy is positive, means shear rate is positive. Okay, because shear rate is a vector quantity, so the if it is positive or negative, that means the direction of the shear rate. Suppose how you check the direction of the shear rate? Suppose this is the direction of y. This is the direction of y. Okay, and the velocity is in this direction. Vx is in this direction. This is the basically the shear rate. Shear rate, you have the perpendicular directions. Okay, fluid is flowing in one direction and velocity is changing in the other direction. Okay, so here the velocity, if the velocity is increasing with positive direction of y, if velocity is increasing in the positive direction of y, then dvx by dy is positive. If velocity is increasing in the negative, in the opposite direction of y, if velocity is increasing in the opposite direction of y, then dvx by dy is negative. Okay, so in this way you can predict that dvx by dy is positive or negative. Okay, because it is a vector quantity. So if dvx by dy is positive, then power law equation will become eta equal to m dvx by dy to the power n minus 1. Okay, and then tau xy will become tau xy equal to minus m in bracket dvx by dy to the power n. Okay, so this is the first part. And second part, if dvx by dy is negative, then eta equal to m in bracket minus dvx by dy to the power n minus 1. Okay, in this case, when you write the tau xy, it will become minus m in bracket minus dvx by dy to the power n minus 1 multiply by dvx by dy, and if you write this equation again, it will become m multiply by in bracket minus dvx by dy to the power n. Okay, so if dvx by dy is negative, you will get the tau xy equal to m multiplied by minus dvx by dy to the power n. Okay, minus will be inside the bracket. Okay, So these are the rules to remove the modulus sign. Now, how the power law equation represent the different type of flows. Okay, so again I am writing the power law equation. Tau xy equal to minus m in mod dvx by dy to the power n minus 1 multiplied by dvx by dy. So there are three cases. Suppose eta equal to 1, eta not, n equal to 1, n is the viscosity index. Okay, n is also called the viscosity index. Okay, if n equal to 1, then this quantity will become, if n equal to 1, dvx by dy will become n minus 1 0. So dvx by dy will become 1, and when this quantity will become 1, then mu equal to m. Okay, so fluid will show the Newtonian behavior. Okay, second case, this is the case 1. Second case, if n is less than 1. Okay, so if n is less than 1, so what will happen? The viscosity will decrease with increasing the value of shear rate. Okay, if n is less than 1, then eta will decrease with increasing, because n is less than 1, then the power will become negative. If power will become negative, then eta will decrease with increasing dvx by dy shear rate. So you have the pseudoplastic fluid. So the behavior will be, so fluid will show the pseudoplastic behavior. Okay, next point, if eta is greater than 1, then this quantity will positive, and value of the viscosity eta, if n is greater than 1, then the value of the eta will increase with increasing the shear rate, and the fluid will show the dilatant behavior. Eta is the apparent viscosity. Okay, so this is the power law model. In this model, you can power law model will show the Newtonian behavior, dilatant behavior, as well as the pseudoplastic behavior based on the different values range of the viscosity index. Okay, so in the power law model, you have, this is the two parameter model. One parameter is m. Basically, m represent the magnitude of the viscosity, and n represent the type of behavior, or how the viscosity will change with the shear rate. Okay, that is the viscosity index. Okay, So if n equal to 1, you have the Newtonian behavior. If n equal to less than 1, you have the pseudoplastic behavior. If n is greater than 1, then you have the dilatant behavior. And how to remove the shear modulus sign? If the shear rate is positive means if viscosity is increasing or in the positive direction of the distance or positive direction of y. Okay, if viscosity Vx is increasing with increasing y, then you have the positive shear rate. If Vx is decreasing with increasing y, then you have the negative shear rate. Okay, so keep it in mind because during the solution we have to check the sign of the shear rate. It is positive or negative, then only we can use the power law model. Okay, I think this is enough for today's class.
Yes, sir.
चलो नेक्स्ट क्लास में फिर
Yes, sir.
करते हैं आगे और एग्जाम की तैयारी कर रहे हो
हाँ, यस सर।
अभी किसका एग्जाम है नेक्स्ट
अभी हीट ट्रांसफर का है फ्राइडे को 9 बजे।
चलो भाई बेस्ट ऑफ लक फॉर ईट की ट्रांसफर